So far, we've seen the problem of respecting someone's privacy, which means basically encrypting a message. Privacy is not the only thing that matters in cryptography. In particular, another essential problem is message authentication. So the problem can be phrased in the following way. Suppose Alice wants to send a message to Bob, and Bob wants to be convinced that the message really was from Alice, and if possible really is what Alice says it is. So the building block of the primitives that will help us ensure message integrity is a hash function. Fundamentally, a hash function is just a function from the message space that we denote by M, and the tag space that we denote by T. And the only thing for now that we assume is that the message space is much larger than the tag space. So this is how you could think of it. You have very long messages, and somehow they get compressed to a tag that has a fixed and a rather small length. So what do we want of a hash function? So since we're trying to ensure message integrity, what we want from those hash function is that it'd be really hard that to find two messages that have the same hash, meaning that once the hashes or the tags differ, then it means that the messages must have been different. Now, of course, it is not always. It's actually guaranteed that there'll be many different messages that have the same tag, and that is just because we've assumed the message space was much larger than the tag space. However, we want that no adversary can find these, which means it's more of a statistical argument. The function is not injective, but we want that any efficient adversary is unable to find two different messages with the same tag. So one way that we can think of using a hash function for message integrity is if a user downloads data from the server. So the server can store on their web page to hash up the software and then offer the software for download. Then the user on their side can hash whatever was downloaded and compare this value to the value that is available and is displayed, the small value that is displayed on the server. And if these two values match, then it gives the user a lot of confidence in the fact that they downloaded the right version and not something that is either the wrong version or even worse, has a virus or something. And if it's not, then the user knows for sure. So if they differ, then the user knows for sure that they did not download what they think they downloaded. Another way hash functions are used is in password verification. So usually passwords are not stored directly on the server, because if it's compromised, then any adversary can see all the passwords. It's a huge security breach. Instead, we use hashes of passwords. And every time we're being asked for credentials, our password that we submit is being hashed, and then the server compares it with the hash of the password. So an adversary who wants to, who for example has penetrated the server can have, like, for example, a pre-computed table of all possible likely, I would say, passwords, especially if these are weak, like if they consist of words from the dictionary with no special characters and no numbers and nothing. So it would still cost a lot of time to pre-compute this table, but once inside the server, it would be very easy to check if a given hash that you find on the server belongs to the table of pre-computed hashes. One way that this can be mitigated is by salting the passwords, which means that instead of storing just a hash of the password, you store the hash of the password concatenated with a string, a random string. That is, so something is chosen by the computer uniformly at random. And in that case, the size of the pre-computed table that one would need to calculate prior to the attack would have to be much larger. So that technique is referred to as hash salting. Now, the whole security of the notion of security of hash functions relies on the notion of collisions, which is finding it must be hard to find two messages with two different messages with the same hash. So everything now will be about assessing the hardness of finding collisions. So finding a collision, these collisions exist. They just need to be hard to find. So the obvious answer to how much work do we need to produce to effectively find one collision is we need to calculate at least cardinality of t plus one different the hash of cardinality of t plus one different messages, and then we're sure that at least two of these messages will have a different hash. Sorry, the same hash. Okay, so that would be a collision. But of course, if, for example, the size of the message is something like 2 to the 128, we're talking about an unmanageable amount of work. But we do not necessarily care about having absolute certainty that we're going to find a collision. Finding a collision with a reasonable probability is bad enough from a perspective of cryptography. In particular, we have a probabilistic method that says that if we want to succeed with probability x, which is between 0 and 1, we need to draw at least that amount of different elements uniformly at random to find that collision with this given probability. So let's keep that in mind. What does it mean as far as the birthday paradox is concerned? So something that we saw in class. A good example of a hash function is the function that takes a person as input and outputs their birthday. So there's only 365 different birthdays. So we can think of finding, we can think of looking for people in the room that have the same birthday as finding a collision for that particular hash function. So if we want 50% chance of finding two people with the same birthday, then we need to draw something like square root of 2 cardinality of t, which is 365, times log of 2 plus 1, and that is about 23. And people refer to that as the birthday paradox because with 365 different birthday and 100% chance of finding a collision, then one would assume that to get only 50% chance, then one would just divide 385 by 2, right? But that is absolutely not what is going on here. In fact, it's more something like taking the square root of 365, give or take some multiples. So it's somewhat counterintuitive, and this is why it's referred to as a paradox, although there's nothing it's not a paradox at all from a scientific standpoint. So now let's prove this formula that I gave you. So suppose n is the number of different DAGs. Let us calculate first the probability of not finding a collision, which of course is just the same as calculating the probability of finding a collision. It's 1 minus the probability of finding a collision. So the probability of finding no collision, essentially, you have n choices for the first DAG you pick, and then n minus 1 choices for the second one, and n minus 2 for the third one, until n minus 1 plus 1, and you divide everything by n to the n. Okay? So that gives you the probability of finding no collision, and then we're going to bound this. So first it equals this value, and then it's because we have 1 minus y less than exponential minus y, then we'll have a product, and then this becomes an exponential with the sum here, of which basically includes the sum of the first n consecutive integers for which we have an explicit formula. Okay, so this goes here, and then there's a minus, and then over n, and then to simplify calculations, we used an equality that this is less than this whole value. So then we want the probability of a finite collision, which is 1 minus probability of no collision, which we just bounded. So to ensure that it suffices, we need to have this inequality, which is the same as, by taking logs on both sides, as this. And which means in the end that n has to be greater than this value, which is what we stated. So then you can adjust the tag, the size of the tag space and the probability you want to derive statements like, with this hash function, what is the probability, how many different messages do I need to draw to have, say, 10% chance of finding a collision? Okay, so these are the kind of questions that you will have to answer during the test. Now, a very standard construction of hash functions is known as the Merkle Damgard construction, and it operates much like the block ciphers in the sense that it's a way to construct a hash function that operates on messages of arbitrary length from one small hash function that operates on blocks of fixed size. So here, the hash function that operates on blocks of fixed size is h. So that h is referred to as a compression function, and it takes as input a tag and an element in a set x, which is corresponds to a block of message, and spits out a tag, which itself is fed in the second occurrence of this block together with the second block of the message, and so on and so forth. A very important feature of this construction is the fact that in the end, the last block of the message needs to be padded, because it's not necessarily a multiple, its size is not necessarily the size of a block. And the padding block, one needs to be very careful, because on top of filling it with trivial characters, one needs to add some information about the message length. Otherwise, it would allow people to create collisions by taking a message that is a suffix of another message, and that would easily provide collisions. So the padding is something that we need to be careful about, but in the end we know how to pad securely, so that this whole construction is secure, provided that the compression function is secure as well. So we currently use mostly the SHA-2 family of hash functions, which has been standardized, and a lot of their names have the format SHA plus some length, which corresponds to the length of the tags. Okay, so you have 224, 256, 384, 512, and then some truncated versions of SHA-512, and that all refers to the tag size. Okay. Now, hash functions only authenticate data in cases where we know the hash hasn't been tampered with. Okay, but the problem is this is not always a good security model. The thing is that the hash function is available to everybody, so everybody can calculate a legitimate tag for some value without requiring any secret. But so, for example, it works in the case of a vendor having a software for download, and displaying the hash on their web page, which is assumed to be a read-only space. But there are other scenarios in which we do not necessarily assume that we're working with a read-only location, and then we need something stronger, which we call message authentication code, or MAC. And a MAC is a pair of a signing function and verification function. So the signing function is very similar to a hash function, except that it requests a key to produce a tag. And the verification function, well, we did not need any of these verification function with the hash function, because everybody was assumed to be able to hash. But in this case, it takes as input the message, a key, and a tag, and decides yes or no, whether or not it's valid or not. So what usage do we have for a MAC? So let's, for example, let's show how we can detect a virus with a MAC. So assume that at a certain time you have a bunch of files on your hard drive. What you can do is you choose a key from the password, for example, and then you will calculate the tags that correspond to the files and your key K. So that gives you, each file gives you a tag, and you assume that at the time you calculate those tags, the files are legitimate. And later down the road, what could happen is that a virus, for example, tampers with the files. But the thing is, this time, a virus can very well tamper with the file and create, say, for example, a file 1 prime, but without the key, the virus will not be able to calculate a valid tag for that new file, which is why you need not just a hash, but really a MAC, because if it were just a hash, then hash functions being available everywhere, a virus could very well calculate a proper hash, but not a proper MAC, because it requires the key, which hopefully you're the only one. Now, what is the MAC security game? Well, it's always taking place, as usual, between an adversary and a challenger. The adversary chooses a bunch of messages in the message space, while the challenger chooses a key uniformly at random. The adversary sends the messages and requests the tags for those messages. So the adversary can request as many tags as they want with that secret key. And then they will compute a message and a tag, hoping, of course, that the tag is a valid tag for that message and the key that was chosen uniformly by the challenger, which the adversary has no knowledge of. And the output of the security game is the verification of this pair. Of course, I should have said this M cannot be any of the M that has been chosen previously by the adversary. That would be trivial, a game that would be trivial to win. So, of course, a secure MAC is one for which no adversary succeed in that game, and of course the advantage of the adversary is just the advantage. This is the probability that the verification checks out. Now, one way of doing a MAC from a hash function is HMAC. So here's how HMAC works. HMAC works with two hashes. So you start with your message M here, and that message gets hashed when concatenated with the key XOR to an inside padding. So you take your key and your padding, and then you XOR these. That gives you sort of like a key prime, so to speak, and then this gets concatenated. So this part here corresponds to all of that and gets concatenated and sent to the hash function here. Okay, so then after you get this first hash, you will repeat the operation to concatenate that output with the same key XOR with an outer padding here. Okay, and then this part here is simply the whole hash of what was previously calculated. And that second hash gives you, by definition, HMAC. And of course, if you want to verify, all you have to do is calculate the tag and verify that whatever tag you receive equals the tag that was proposed to you. Okay, so this is a secure way, as long as the hash function is secure, of course, to create a MAC. You can always also think of MACs from PRFs. So assume that you have a PRF, and you can define a MAC by basically evaluating for the signing function to evaluate the PRF at the message and the key, and verify by basically calculating the tag and verifying that the tag that is proposed is actually the tag that would have been calculated by the PRF. And there is a way to tell if a PRF is secure, then that sort of MAC will be secure, assuming that there are enough different tags that are possible. So we're not going to prove this theorem, and for the most part we're referring to HMAC, but it's a good thing to know that any PRF could result in a secure MAC. So that's all for this time.